Okay, hi. I'm Stephen Buss. Sorry, let me just get this set up. Okay. So, hi, I'm Stephen Buss. I'm that lost. Okay. I'm a software engineer on the Go runtime for App Engine Standard. I work at Google in San Francisco. And I work on the Go runtime. Thank you so much for having me. I really love Japan, and I'm happy to be here. I'm sorry that I don't speak Japanese. If you want me to speak slower, just raise your hand, and I'll try to adjust. But I think this will be online afterwards, and maybe I'll get Yoshi to write some subtitles for it. Okay, so I'm going to give you a brief overview, a brief history of Google App Engine, including some of the difficulties that we've faced in the past. And then I'll tell you about the new runtime, which lets you run regular, unmodified Go programs on Google App Engine. So Act 1, the beginning. App Engine was the first serverless computing platform. It launched in 2008 with Python, and then in 2011 we launched Go with version R57.2 before Go 1.0, and that was because we launched before Go 1.0. We made a few design decisions that might be a little weird now, but they've persisted. And we launched with a couple limitations similar to what you saw with Python. So you have no unsafe package, no sockets. You don't have a real file system. Instead, we patch in a virtual file system and we whitelist a few specific paths. But most file system operations and most paths will fail with EPERM, right? Permission denied. We also replaced syscall with a very limited surface. I'm sure if you've ever played around with syscall stuff, you are pretty aware of that. And finally, we limited programs to a single thread. We optimistically thought that we would fix it soon, but that didn't happen. So the execution and billing models all assumed one request leads to one thread. That was inherited from Python, and it made assumptions on our side easier. This was partially to prevent DOSing the platform, either from malicious programs or poorly written programs. But it ultimately meant you could run a single thread. You could run Go routines, of course, but they weren't parallel. Right? So App Engine's whole purpose is to run untrusted code on Google servers with no virtual machine required. So what could go wrong, right? We're running your code on our servers, it's fine, right? Well, no. A lot can go wrong. And so in addition to limiting the standard library of Go, we ran apps in a multi-tiered sandbox to keep customers safe. So I'm not sure if we've talked much about this before, so this might be some new information. Python had this clever approach, Python and App Engine. In addition to the hardware and network isolation at the data center level, we also used NACL from the Chrome project, the Google Chrome browser, right? The NACL sandbox, and ptrace from the Unix kernel to provide two levels of security for your app at the system level. So NACL was developed by the Google Chrome team to securely run compiled extensions on users' machines. Unfortunately, it requires that developers link against NACL, and it gives programs limited access to system resources. It was really quite excellent when it was created, but it's been kind of a headache to develop with over time and has been a large factor in why development on App Engine, for the reason that we've missed a couple releases. So we actually aren't using NACL and ptrace anymore on the next generation, second generation runtime. Instead, we're using gvisor, but I'll talk about that in the second half. So if you're not familiar with ptrace, it's from the Linux kernel, part of the Linux kernel. It's a syscall that gives a program the ability to intercept and modify syscalls of other programs. It's most commonly used with a debugger. So, right, a debugger will you attach to the process, you set a breakpoint, and that's ptrace basically. So it allows you to step through, intercept every syscall, jump around the program, change what's being called. So we use that to intercept and inspect every syscall that gets made by your app on App Engine, and we will crash your app if it does something that it's not allowed to do. So obviously this is going to be a bit slower than running in a virtual machine, but it gives very good performance, and you can pack a lot of things onto one machine. So in order to run Go under NACL and in our limited environment, we had to patch the standard library and build with CGo, because NACL is a C library, right? So for example, I mentioned the virtual file system earlier. So one of the limitations in the environment that we have on the legacy runtime is the virtual file system is not pollable, right? So when with Go 1.9, it combined net/poll and the OS, I think it was an OS package, polling mechanisms into a common interface, and that didn't work. It crashed. It caused random panics. So that was pretty much why Go 1.9 was late, because I had to fix that. We also disabled a lot of syscalls. We only allow a small subset of syscalls that we deemed safe. And we patched Go, the Go standard library, to use an internal syscall package that is specific to App Engine. So if you play around with the runtime, and you'll discover things like chmod, makedir, rmdir, kill, etc., are all disabled, and they'll return eperm, permission denied. So in addition to that, we also have network isolation, which I'm sure caused you many headaches. We don't allow apps to open raw sockets, right? Instead, we intercept socket calls and redirect them. So network calls go from your app. We intercept it, and we forward it over a Unix domain socket to a controller program that's running on the same machine. We then send that through a network proxy, which allows access to internal APIs. So this enables really cool things like automatic authorization for API calls, but it also means you have to use the URL fetch package rather than net/http.get. And it also means you can't do things like run a gRPC server on App Engine, because that requires opening a raw socket. Also, we require all traffic be HTTP, and so that's another factor that prevents you from running a gRPC server. So as I mentioned earlier, we use ptrace to monitor all the syscalls your app makes. So I'm going to give you a little demo of how ptrace works. But first, I want to give a big thank you to Liz Rice. This example I'm going to show you is a slightly modified version of her code. She gave this excellent talk at GoCon 2017 called A Go Programmer's Guide to Syscalls. So I really encourage you to go watch her talk. It's excellent, and read her code. I learned a lot from it, and she goes into much more detail than I will. So let's switch to the Oh, I gotta exit the presentation. Nope. There we go. Trying to figure out how to zoom. I see what happened. Yeah, I'm doing Control Plus. There we go. Okay. Can you read that? Is that good? Okay. So I have a simple ptrace example. I'm going to have a controller program monitor the execution of a simple hello world program. So I'll open it in Vim. So here's the program. It's very short and simple. So all it's going to do is print hello world. And then it's going to open a file, foo.txt, and then it's going to read it into a buffer and print the contents to the screen. So the controller program is the interesting thing. First, I'm using this libseccomp Golang project. It's not necessary, but it allows you to write platform-independent code that uses ptrace. So, I should comment this out. So it's very simple. We're just going to read the command from the terminal, from the command line, and the important part is we're setting ptrace true on sysproc adder. That will enable the ptrace syscall. Then we just start the command and wait on it. Grab the PID, and then we enter an infinite loop. So this will read the registers for the program that is executing. It will read that into a struct, syscall to ptrace regs, and then we want to get the syscall ID from orig rax. So that contains the original syscall that was executed before ptrace intercepted the call. We get the name using that platform-independent seccomp package. That will give you different results depending on the architecture that you're running on. So syscall ID is obviously different under Windows and under Linux and other operating systems. And then I'm just going to print the ID and the syscall itself, and then allow the next syscall to happen. So you resume operation by calling ptrace, and then it will run the next command and then throw a sig trap. So we're going to wait on it and then intercept, catch the sig trap, and then we loop. So let's show it. Let's show it in action. So I'm using GoMod and I'm on my GoPass, so I'm going to turn that on. Okay, great. So I'll just go way to the top here. Okay. So I run it, and you can see immediately the command.wait returned a trap, the sig trap. So that's where we start the infinite loop. So then this is all just set up from the Go runtime itself. That does a lot of RT-sig action. Okay. Then now we're getting to the end of the setup for the Go runtime. Okay, here we go. So you can see it calls write, and then writes hello world, and then resumes the write operation. So interesting thing about ptrace, when you intercept system calls, it will give you a handle before you enter it and then after you leave it. So you can do things both on entry and on exit, which is why you see every syscall is repeated. Okay, so we write hello world to the screen. Then we do that, right? We opened, all right, I missed that one. So open at opens the file foo.txt. We then write to the screen that we opened it successfully. Then right here we read the file, and then we write the contents, which is bar, with 2 new lines. And that's it. So that's the basics of how ptrace works. So let's disable a syscall. This is one of the security measures that we use in the legacy runtime. So I'm going to disable open, so you can't open files. And that's really simple. You just use the seccomp package to get the syscall ID of openAt. Then you create a filter that allows everything, and then this disables the syscall ID of open. And then we load the filter and then continue on as usual. So I'll save that. We'll run it again. And you can see things are different. So we got through hello world, we wrote it, then we ran openAt, and you'll see openAt entered and exited, and you'd think that, well, it succeeded, but actually it returned an error, right? EPERM. We've got operation not permitted, permission denied. And that's how you disable syscalls that you don't trust with ptrace. You can do more advanced things like inspect the arguments. So, like I said, we whitelist specific paths on the file system. So I could check the path that you gave to open and allow it or deny it based on that argument. But that's beyond the talk for today. Okay, cool. So let's go back to it. Okay. So sorry. Okay, so beyond these didn't mean to do that. Beyond the security features, we also want to provide a good user experience, and that means a couple key features. The App Engine has no need for package main, which is still true for all the way up through Go 1.9, but it is not true for Go 1.11 because now we run regular unmodified Go applications. So this no package main is not totally crazy. In fact, Google Cloud Functions, which is launching Go support soon, has the same support. You just write a function, you give it to Cloud Functions, and it builds a main for you, and we do the same thing. This is neat, but it also means that Go App Builder, which is what we use to build your Go applications, it diverged over time from Go Build. And in fact, I believe we launched before Go Build even existed. It was compile and link at the time, if I remember correctly. So this is the primary reason that we never got support for vendoring. So Go App Builder, because it was separate from the Go Build command, we had to re-implement everything that it did. And because it spent 6 years getting farther and farther apart, we never could add support for Go vendoring, though I did try and failed. So we also support apps that aren't on the Go path. That's another thing that's still true, because with Go 1.11, you can use Go modules, and that doesn't require Go path. We, over time, of course, added the App Engine package to the standard library, which gives you access to all the cool App Engine APIs. And you could maybe call this a feature or not, but we had no support for net/http.listen and serve. That was because no raw sockets, right? So if you've used App Engine, you're familiar with calling appengine.main. So behind the scenes, that calls into the internal App Engine package, sets up the web server for you using the limited network stack that we provide, using some tools that we don't expose to customers. So Go on App Engine had a great start back in 2011, but Go has changed a lot since then, and we haven't always done a good job keeping up with Go. So Act 2, the journey. There was a lot of development from 2011 to 2015. The original development team did a really amazing job, and I want to give a lot of credit to them. They were great, but they added support for all of the App Engine APIs. They open sourced the App Engine package to google.golang.org/App Engine. They improved the performance and security of the sandbox over time, and they did accomplish several version upgrades of Go. So in March 2012, the Go 1.0 launched. That was about a year, I think, after we launched on App Engine. And that was the first of only 2 times, sadly, that we launched on time. The other was Go 1.2. That was about, I think, a year and a half to 2 years later, before the regular release cycle started. And as many of you already know, we entirely missed Go 1.3, 1.5, 1.7, and 1.10. So believe me when I say it wasn't for lack of trying. Why did we miss so many? So the NACL environment was the one of the biggest reasons. Besides, the NACL environment was the biggest reason that we missed so many releases. Developing for NACL is difficult, and maintaining the patches to across Go versions while ensuring the security of the platform is a big undertaking. So, for example, I missed Go 1.7. That's my fault. Because the patches from 1.6 did not apply cleanly to 1.7. And so it required several weeks to get the environment patched correctly. And then when we tested it, it would have random panics and was just a very unstable, unusable system. So we spent a couple months getting that correct, getting everything working. And by the time we were ready, Go 1.8 was only a month away. So we made the hard decision to skip 1.7 and just go straight to Go 1.8. So that was my first launch on Google App Engine. A failed launch followed by a successful one. So even when everything goes well, we still have to build on the golden release of Go. So that means we have to wait until the Go release is ready and public before we start validating the runtime. So that guarantees about a month delay between when Go comes out and when we have it on App Engine. The good news is that with the second generation runtimes, that should come down to a week, maybe 2, if we're unlucky. I shouldn't have said that. Also, I missed Go 1.10 because after Go 1.9, we moved all of our development resources to the second generation runtime infrastructure. So no one was working on getting Go 1.10 to work on App Engine, the legacy runtime. And so when the second generation infrastructure was not quite ready, we had to wait. So sorry about that. But hey, the good news is Go 1.11 is out. It's still in beta. I'm still fixing a couple bugs. But when in the future, adding new versions is as simple as editing a config file, running the build, and then validating the runtime. We don't have to patch anything. We don't have to do the same level of security analysis. I mean, we still, of course, make sure it's safe. But because we're working with unpatched code, our security review is much easier. So in addition, we missed releases because the Go 1 promise, the Go 1 compatibility promise, doesn't quite always live up to its goals. So the Go 1.4 to 1.6 upgrade broke some customers. And so we halted development on new features and instead focused on adding support for multiple versions. That was my very first feature. I added support for pinning to a specific version. So starting from the next release after Go 1.6, which was Go 1.8, allowed you to stay on Go 1.6 until you were ready to upgrade. So that, of course, made us miss Go 1.7 because we were working on the pinning support. Okay, so that's how we got here. Let's talk about what's ahead. Act 3, the next generation of App Engine. The biggest change behind the scenes is gvisor. And it's the one I am most excited about. No longer do we have to worry about NACL and ptrace. We get to use gvisor, which is a public open source project, which you can find there, github.com/google/gvisor. It's super cool. You should check it out. So gvisor is a user space kernel written in Go that implements a very large portion of the Linux system surface. So like ptrace, it intercepts system calls and acts as a guest kernel. Unlike our ptrace environment, where we had to patch Golang syscalls, the Golang syscall package, and to re-implement the syscalls that we needed, gvisor allows us to safely use any syscall that it implements in a totally natural way, which means running stock, unmodified Go. So in addition to a real kernel, you also get a real file system. So the file system syscalls that I mentioned before that were disabled in the old runtime, chmod, makedir, etc., now all work correctly in a completely isolated environment. Note, though, that this is still a serverless runtime, and so your file system is temporary. It will only exist for a limited time, and then eventually when your app gets restarted, the files are gone. So if you want to persist data like before, use data store or Google Cloud Storage or something like that. So gvisor enables us to securely run untrusted code on our infrastructure without building against any special libraries like NACL. So rather than using a custom version of Go with a patched standard library and a custom Go app builder, we can now run Go build. That's all it does. So you run Go build on your laptop, we run Go build on our servers. It's exactly the same. Nothing is weird anymore. So gvisor is better than ptrace and NACL, definitely. But why is it better than a virtual machine? So it comes down to resource usage and an extensible architecture. So gvisor can operate on machines with limited CPU and RAM. Or, to put it in another way, we can pack a lot of apps using gvisor onto a given machine. So than if we were using virtual machines. This leads to higher performance and lower cost than you would otherwise get. So I'll talk a bit more about the extensible architecture in a couple slides. Not everything is perfect, though. I'll admit. gvisor has a few drawbacks compared to a virtual machine. Foremost is the reduced compatibility. You're not actually running Linux, right? You're running a guest kernel, whereas a virtual machine is running a real Linux kernel. In practice, this probably won't be a problem, but the gvisor team is constantly working to expand its syscall coverage. And also, it's open source, so if it's missing a syscall, go ahead, go implement it. We would gladly accept pull requests. It also has a slightly higher syscall overhead than a virtual machine, but it's no worse than the old generation. Most relevant to you as developers on App Engine is you might experience a unimplemented or buggy syscall. These are very rare, but if you see them, they are hard to debug. And I'm sorry about that, but it is improving every day. And if you find something weird, just open a bug. We'll figure it out. So the basic idea of gvisor is simple. You run an untrusted binary on a guest kernel, which acts as the sandbox. So depending on the syscall, gvisor re-implements every syscall. Though for some syscalls, it ends up simply calling the same syscall on the underlying system. That's just because it's safe enough that we don't need to do anything special, but it does intercept every syscall. So this kind of functions like ptrace. In fact, it functions exactly like ptrace, in that all syscalls can be inspected, but rather than killing a process or returning permission denied when you use a dangerous syscall, it instead gets a safe re-implementation that only runs inside the security sandbox and doesn't touch the underlying system. So I'm going to switch to show you the same hello command running in gvisor. So this one's not going to have anything disabled, but I'm going to show you how it's similar to ptrace. So I have a simple Docker file because gvisor is a driver for Docker. So you can run Docker images using gvisor, and it runs in a very safe, isolated environment, whereas Docker, well, I won't say anything bad about Docker, but gvisor is safer. So I'm just going to run this Docker file. It's just going to, copy the command in and read a file. Right. Okay, so that ran, and nothing is neat there, but, oh, you're right. There it is. Okay. Live demos. So I forgot to show you the configuration for Docker. This is how you use gvisor in a Docker environment. You add this runtime config for runsc, it's run secure container, and you point it to the binary for runsc. That is gvisor. This is turned on for the demo, the debug logs. So this is going to be similar to the logs I showed you earlier. And the one we care about is this boot log. This is going to be hard to read, so I'll scroll down a bit. But this is the logs that gvisor generates. This is all setup stuff, but now you can see it sets up some syscall filters. Some of these are re-implemented. They're all re-implemented. We just scroll way down. Let's search for hello world. Okay, so here we're going to see something really similar to what I showed you before. We've got the hello syscall. This time it logs the arguments. So it's logging hello world as the argument to write. We let it proceed, and then that's the exit from write. Here's the open syscall that I showed you before, and this time it has the argument /foo.text. So this is how you would disable particular paths if you wanted to do that. gvisor, you don't need to do that on gvisor, but you totally could. And then this just runs normally. So it's, as you can see, it's super easy to use. The logs are very verbose. It takes a while to figure out how to successfully read them. But it works just like regular Docker. Like it ran and it printed the contents of the file. All right, so that's gvisor. Oh, right, the extensible architecture. This is super cool. gvisor does this really cool, clever thing. So devices and files can be implemented as what we call gophers. Just to make things confusing, we chose the same word. These isolate external communications from the secure kernel. So this allows both security isolation, so that, for example, the mistakes in the network stack or something malicious can't escape the network call and hit the kernel. It's completely isolated. And it enables special file handles. Like in App Engine, we have /cloud SQL. And that allows you to open a connection via a Unix socket that actually goes out over Google's internal network to your cloud SQL database and read and write to your database with no configuration needed. It just operates like a regular Unix socket. And under gvisor, rather than patch, net, and OS packages, we can instead, like I said, run unmodified Go. The syscalls are handled by the Sentry. So the Sentry is the kernel, right? And the Gopher does all of the file system and network communication in Google, in production App Engine. So I can't praise gvisor enough. It's really great. You should all go check it out. Again, github.com/Google/gvisor. It's really, really phenomenal, and it powers this second generation App Engine runtime. Okay, so gvisor is awesome, but how does that translate into a better experience on App Engine? So this is the old way. You're all familiar with this, probably. This has, you import google.golang.org/App Engine, and you call appengine.main. And that's how it works, right? There's no listen and serve. There's no raw sockets. The new way is better. I mean, it's normal, right? You import net HTTP. You run listen and serve. You read the port from an environment variable exactly like you would do on your laptop or on your desktop. And this, of course, makes it so that you don't need to use dev app server or Go app. You can just run Go run. That's good. That's one of my favorite features. Right, so I'm going to give you a little demo of the old way and the new way. So, okay, so this is a simple hello world in the old way, right? It calls appengine.main. It runs. It prints hello world for the handler, and then it prints the Go version. Totally simple. Things you've seen before. This app YAML, I'm sure, is very familiar. I'm not actually going to deploy it, but I'm running this just so I can get the URL. So here, right, this is it running in production, Go 1.9.4. Yeah, I know it's outdated. So that's the old way, right? Okay. So if you look at the new way, this is regular Go, reads port from the environment, defaults to 8080, runs listen and serve, and then it does the same thing as before. And the app YAML is different. It's just runtime Go 111 with a service, new hello. So this is pinning by default. In old App Engine, you would have API version Go 1 or Go 1.9. In the new version, it's always version specific. So Go 111 is Go 111. Go 112 will be Go 112. I don't know what we're going to do when we get to Go 11.1. We'll figure it out. So if we deploy it, I'll let it run in the background, but I'm also just going to open it up. So I deployed this earlier, and you can see it's a regular Go program. It's running Go 1.11.2, which, hey, look, it's modern. It's the same version that's live. This will take a minute or so. And you can, of course, run it locally with Go run. I'm seeing my search history. What happened? Oh, right. There it is. Not using dev app server. Although you totally could use dev app server if you wanted it works. But you don't have to. The whole point is make it easy, right? You can use your current workflows, dev app server, etc., and migrate to this new generation of runtime. And the deploy should have finished by now. Yeah, it doesn't take that long, but that's it. Oh, vendoring. I'm really excited about this because we actually support vendoring now. So I'm sure you've all seen this horrible error message in the past. App file foo.go conflicts with the same file imported from GoPath. That happens when you vendor because of the problems with Go App Builder that I talked about before. So this just does simple, it vendors one function that just prints in at the index handler. So we go to the new example. It's the same app, right? It's the same thing. This time, of course, it's not using AppEngine.main. It's using listen and serve. It's a regular Go program. And if you wanted, you can run it with dev app server. And if we reload this, you can see vendoring works. Hooray. And you could deploy that, and everything will work normally. I'm gonna, go ahead. Of course, it still works in production, and it works exactly like you would expect. What happened to my... All right. Oh, I forgot one thing. We also support Go modules. So we are at the bleeding edge of Go, so you can have an app that uses go.mod. I forgot to show that, so Go mod, a simple app. Doesn't do anything special, but this also works with dev app server. Right, cool. Okay. So, you get all this good stuff, but there's got to be a catch, right? Well, yes. You should start migrating away from the App Engine APIs. Instead, you should go use the cloud APIs, cloud.google.com/go. The old APIs are walled garden, so you have to use App Engine to use them. And that's not great. That means that you are stuck on App Engine. You can never move away. So by using the cloud APIs, you can go from App Engine to Kubernetes to virtual machines. You could even use competitors, but you can still use the same code anywhere. We no longer have the same limitations that we used to have. It'll take a little bit of work, but it will be totally worth it. Check out these APIs, these URLs to look at migration. The second one is the Go doc, and the first one is more, they're better docs. Okay, so I'm really excited to be working on the runtime and to be working on Google Cloud. I love Go, and the future of cloud at Google is built on Go. All of these products are written in Go, from gvisor, which is the core virtualization technology for App Engine 2nd generation, to the runtime itself. The Go runtime is also written in Go. In fact, every runtime for 2nd gen is written in Go, including Python and Node and whatever else we'd have. Google Cloud Functions is launching the Go runtime soon, and you should check out the GopherCon 2018 talk by Kelsey Hightower about Cloud Functions. He did an excellent job. It's a really cool product. Check it out. I don't know when they're launching, but it's soon. And of course, Kubernetes and Knative, all written in Go. Every important cloud infrastructure piece is written in Go, and there will be many more. I wish I could tell you about all of them. So there are Right, so yeah, they're all ready to go. So that's it. I'm, again, really happy to be here. If you have any questions about App Engine, pull me aside. I'll be here, walking around. Happy to, like I said, happy to answer any questions you have. Right, no, one more thing. It may have taken 7 years, but Go Max Prox is no longer one.
Oh.
You can run. You can run parallel code. Okay, thank you so much, and have a great rest of the conference.